Hey everyone, welcome back to another video lecture here for Managerial Economics. This is Finance 30210, and today's topic, we're going to talk about game theory. And so we're going to begin with our idea of game theory and how we can introduce some of the defining characteristics of what we see in a game. So for any game to exist, we need three things. We need players, actions, and payoffs. So players, we can think of these as either firms or individuals. Now these firms or individuals are going to be acting rationally. That means they're going to be profit maximizing or utility maximizing. Now this analysis will change a little bit if we understand that firms are risk loving rather than risk averse or risk neutral, which we expect them to be right now. But for this class, we don't have to worry about that. Actions then are going to be chosen by each player. Now, actions can be things like throwing rock or paper or scissors in the game rock, paper, scissors, or choosing left rather than right, or to price a good before your competitor does, or enter a market before your competitor does. All of these would be considered actions or strategies. So depending on the style of game that we're playing, we could play a one-shot game where it's just one choice that we're making, or we could play a repeated game where we're making multiple choices. We'll have a strategy set. So payoffs are the last thing that we need for this game, and payoffs include things like profit or money or utility or prison time even, or just winning the game. And so we're going to calculate payoffs in a variety of ways, and one of the most common ways to kind of calculate payoffs is through something called the expected value. Think of expected value as a lottery, so to speak. If you play the lottery, with some probability you'll win, although it's very low, there's some probability, and you'll win some amount of money. And then on the other side, you have a high probability of essentially losing, and you're going to lose some amount of money. So if I add up the probability of winning times the amount that I'm going to win, with the probability that I'm going to lose times the amount that I would lose, that would get me my expected value of that payout or that lottery. We could also think of this as flipping a fair coin. So the probability that we have of, the probability that we see of heads coming up is 1/2, and the probability of tails coming up is also 1/2. And so if we denote the probability, if we denote the probabilities as such, and we also then say the outcome of heads is going to be binary, it's just going to call it 1, and the outcome of tails is going to be 0. Well, what is then the expected value of getting a heads or flipping this coin? And so this expected value is just our probability times our payout of 1 plus the probability of flipping tails times the probability or times the value of our tails takes. And so our expected value is 1/2. So 1/2 the time we flip heads, 1/2 the time we flip tails. And that fits with our intuition here. So as we move on, we can talk about different styles of games. Games can be played in a variety of ways. The two that we are going to focus on are simultaneously played games and sequentially played games. Now, simultaneously played games are those where players choose their strategies at the exact same time, and they have full information not only about the expected payouts, but they know what their payout is going to be given the choices that they make and the choices that their opponents make. So we can think of this as the card game War. So you flip over when you have a war, 2 cards are equal. You put down the next 3 cards, then you simultaneously flip the last card. And you know what the payout is going to be. You get all of your opponent's cards if your card is higher than theirs. So that is the action, and those are the payoffs that we can look at there. And then rock, paper, scissors is also another simultaneously played game. Whereas sequentially played games take turns. So player 1 might choose first, then player 2 observes what player 1 chose, and then player 2 can choose accordingly. We believe that all players, again, have full information, not only about their action set, but about the payoffs. We can think of this as any board game, really. Chess, checkers, Monopoly, things like that are going to be played sequentially. So depending on how many times we play these simultaneous or sequential games, we have another name for that. So The first is a one-shot game. Now, a one-shot game can be either simultaneous or sequential, but the game is played only once. Now, this is going to become really important when we're determining the best course of action, because if we never have to play with that other person again, maybe there's an incentive for us to cheat the other person. Whereas a repeated game, we can see that if we're going to be playing more than once with the same person, not only would we be disincentivized from cheating if we want to cooperate, but we might also be able to notice or pick up on patterns of what this person is going to be playing, what actions this person plays. So I think these games, these repeated games and one-shot games give us another dimension to analyze what's going on here. So once we start working with these games, we can talk about two different things as well within the game, the outcomes. One is called a strictly dominant strategy. Now, this is really interesting because a strictly dominant strategy just says that a player will choose one action since that action results in a better payoff than any other choice they could have done. And that's regardless of what their opponent chooses. So the strategy occurs when the payoff is to playing one strategy is always preferred. So this is a really interesting dynamic, which is going to come up every so often, which we'll see in class. And then the next kind of, what are we getting towards? Kind of the end result of a game. How do we know kind of the game is finished or the choices we've made result in the end of a game? And this is where the idea of a Nash equilibrium comes up. We talked a little bit about this Nash equilibrium, but really we want to flesh this idea out because it's very important. We actually call this a fixed point theorem, but really the Nash equilibrium just says that no player can improve upon their payoffs by switching strategies once they know what their opponent has chosen. So, like rock, paper, scissors, I would not want to, if I threw rock and my opponent throws scissors, I would not want to change my strategy. But my opponent, who threw scissors, knowing that I threw rock, would want to change their strategy. Therefore, that can't be a Nash equilibrium. So we're going to search for and find the Nash equilibria in these games. That's what we're trying to look at. The one thing that we want to kind of reiterate is the assumption that when players are making or seeking outcomes or looking at actions, their anticipated behavior, since it's deemed to be rational, actually becomes their behavior as they play the game. So I'm going to reference player 1 believes that player 2 is going to choose one action. Well, when they believe they're going to choose that action, in reality, we believe they actually choose that action. So that's kind of notation and phrasing you'll hear as we solve these games. Now, for you following along right now, you might want to take a minute, 6 minutes actually, and watch this YouTube clip. It's called the Golden Ball Game Show, and it's a game show out of the UK. But if you don't have the time to watch the video, I'm going to describe it to you really briefly. So, the game starts with Abraham and Nick. Now, Abraham and Nick are going to be playing against each other. What they're playing for is a non-trivial amount of money. So their payoff is $13,600 or some variant of that. Their strategies can be to split or to steal that payout. So how do we go about understanding what are the outcomes? They have two actions, both of them, to split the payout or to steal the payout from the other one. If they both split, if they both choose simultaneously to split their winnings, they are both going to get a payout of $6,800. But if one chooses splits and the other chooses steal, then the person who chose split gets nothing. The person who chose steal gets all of the money, $13,600. Now, if they both choose steal, they both get nothing as well. So up until this point, Abraham and Nick have played this game together. Now, they played it together, but this is the very last game that they're playing. So they've built up some goodwill, but this is the last game. We're going to call this a one-shot game because they don't have to play it again. So how can we better understand this information? There must be a more succinct way to kind of aggregate all of these results, and there is. So in this table, we have Abraham and Nick's payouts. Abraham is going to be in black. So Abraham has two choices, to split or to steal. And we can see that here. So we can split or steal. And Nick has the option to split or steal here. So we can see these right here. Now, like we discussed, if Abraham chooses split and Nick chooses split, they're both going to split the outcome, which is 6,800 each. So we're in this cell right here. If Abraham chooses split and Nick chooses steal, we notice that the stealer gets all the money, so they get 13,600. And we have the same result here. And if they both steal, we said that they got nothing. So how do we find the Nash equilibrium of this game? That's what we want to look for. Where is the Nash equilibria? I'm going to just label that NE, the Nash equilibria. And again, we want to remind ourselves that this is the spot where no one wants to deviate once we know what the other opponent is playing. So if I am Nick and I believe that my opponent Abraham is going to split, we want to think about what my best option is. And so if I'm Nick and I see this split, I'm going to determine I should then not split but steal, because 13,600 is better than 6,800. So we don't want this choice at all. And now if I am Nick and I believe that Abraham is going to steal, my best option now actually becomes to either split or steal. I am indifferent because I get zero either way. So I have no strategy that we're going to call dominant. And that is because I'm going to be indifferent or choose split or steal depending upon what Abraham does. Now let's look at Abraham's beliefs. Now if Abraham believes that we are in this column, if Abraham believes that Nick is going to split, well then that means Abraham's best option is to steal. So they're going to get 13,600. And if we believe we're in this column and Nick is stealing, that means Abraham believes Nick steals. So my best option, well, I'm indifferent between splitting or stealing. And so we're going to look at where both players decided to play together. So that happens in three categories. So the three Nash equilibria happen where we have steal, split. Again, that's Abraham choosing steal and Nick choosing split. We have split, steal. And again, that's Abraham choosing split and Nick choosing steal. And then our last is steal, steal. These are our three equilibrium outcomes. So this is really interesting, and you'll see if you watch the video that they actually are able to talk to each other, and Nick and Abraham are pleading with each other to choose one versus the other, and ultimately actually choose to split. This is the ideal outcome for both players, to actually split the pot, but we see that this isn't actually a Nash equilibrium. So it's interesting that they were able to get to this outcome because we would think that they would have a very, very, very high incentive to deviate. Because if Nick believes that Abraham is splitting, Nick would want to steal and get more money, 13,600. And if Abraham believes that Nick is going to split the pot, then Abraham wants to deviate from his choice and take the steal. That's why we believe these can't be Nash equilibrium. They would rather the higher payout. Okay, So let's work on a different prisoner's dilemma type problem, as we'll discuss. So suppose you and a group of coworkers have decided to have lunch at a Japanese restaurant. It's been decided in advance that the lunch bill will be divided equally. Each person in the group is concerned about his or her share of the bill. Without talking or explicitly agreeing to do so, what will the group decide to order, high-priced items or low-priced items? We're actually going to first look at just you and a friend going to eat and see if that changes at all. So what might this payout look like, or what might this structure look like? So you have you and your friend. So your choices are here highlighted in yellow, and your friend's choices are highlighted in blue. So the payouts are going to be in blue for your friend, and your payouts are going to be highlighted again in yellow. So how do we determine what is the best course of action for ourselves? Well, when we start looking at these payouts, we will need to determine, when I choose a low-priced item and my friend chooses the low-priced item, we both are going to just pay for our low-priced items. We want to know if that low-priced item, when my friend chooses it, is that going to be greater or less than the high-priced item in terms of my responsibility? Well, I believe that this is true. I believe that we're going to find this condition, that the price of the low price item will be less than the price of the high priced item plus the price of the low priced item divided by 2. So if we were to split that, that kind of intuitively makes sense. But we can see the math over here, that if I have 2PL, that it's going to be less than PH plus PL, right? I'm just separating out this inequality. So we start with our condition on the left. So I split this inequality up, and then I simplify, and I get this answer that the price of L will definitely be less than the price of H. So as long as this is true, which I think it is, that's our assumption we're making, then it'll be the case that the low-priced item will be less than the splitting the high-priced item. So if that's the case, I'm going to choose this when I believe my friend is choosing the low-priced item. And if my friend is choosing the high-priced item, we need to figure out what is going to be bigger. So I think that PH plus PL divided by 2 is going to be less than PH. Now again, I do some algebra, and I do the algebra, and I get that PL is indeed less than PH. So I know what I believe to be true, so that means when my friend is going to choose the high-priced item, I'm also going to choose the low-priced item. So here we have a dominant strategy. The dominant strategy is for you to always choose the low-price item, regardless of what your friend is going to choose. And now we can think about the beliefs of your friend and you. If your friend believes that you're going to choose the low-price item, what might they choose? Well, again, they're going to choose the low-price item. And if your friend believes that you're going to choose the high-price item, what might they choose? Well, they might choose, they're going to essentially choose the low-price item as well. So we're going to erase this. Sorry, real fast. We're going to choose a low-price item. This is what I wanted to circle. So this low-priced item is what our friend is going to choose, and we can see then that our Nash equilibrium must be PL, PL, right? Low price, low price. This is our outcome. And so we'll always choose the low price items when faced in this scenario. So does this change, though, as we have more and more people? And I urge you to kind of go through this same analysis. What is my belief? What is my action when my belief of my competition, what they're going to do? And we actually get the same exact result here, that we'll always choose the low-priced items. Okay, so let's talk a little bit more about repeated games. So these past games have all been single shot. Now repeated games, like we believe, are going to be played more than once. So how does that change? How does this information change for us? So we have two players. We have player 1 and player 2, and player 1 and player 2 both have actions. So this will be player 1. This will be player 2. Player 1 can choose left, middle, or right, and player 2 can choose left, middle, or right. And we think that these payoffs are in millions of dollars. So if both players choose left, they both get $1 million. So we want to know where the Nash equilibrium are. So let's first suppose we're playing this game once. So if we play this game once, we want to think about our beliefs. So if I believe that player 2 is going to choose left, it's in my best interest to choose left because we know that 1 is greater than 0 if we chose right or middle. If player 1 believes that player 2 is going to choose middle, my best option again is to choose left because 5 is going to be greater than the 4 is going to be greater than the 0 if I chose middle or right. And if player 1 believes that player 2 is going to choose right, then I'm going to choose right because I believe that this $3 million is better than nothing if I were to choose middle or left. Now we have to do player 2. If player 2 believes that player 1 is going to choose left, well then they're going to choose to play left because this 1 million is greater than this 0, which is greater than this 0 if they played right. And if player 2 believes player 1 is going to choose middle, they're also going to choose left because it's bigger than the 4, which is also bigger than the 0. And player 2 believes that player 1 is going to choose right. Well, they're also going to choose right because they believe that this 3 is bigger than this 0, and it is also bigger than this 0. So now we look where the two boxes match up, which means that we have two Nash equilibria happening at left, left, and right, right. But is this the best outcome? So if these are our two Nash equilibria, is there a better outcome that we could have achieved? And I think there is. We would both be better off if we played 4-4. This is the joint profit maximizing outcome. If we were to decide on the jointly profit maximizing outcome, it would have been middle, middle. So we want to play here. We would rather play middle, middle than any of our other two options because we are certainly worse off. But we can't just play middle, middle because there is a very high incentive to deviate. If we tried to play middle, middle, then we could see that if player 2 plays middle, player 1 wants to deviate and choose left because that 5 is greater than the 4. And if player 2 believes that player 1 is choosing middle, we believe that they're going to deviate and choose left again. So if both players deviate, they're going to choose left, left, and they're going to end up back at this Nash equilibrium. So is there a way that we can choose this middle option without having, with this being a Nash equilibrium? There is if we decide to play repeatedly. So we can now play this game twice, knowing that there are two Nash equilibria to begin with. So we're going to set this up. This is our first Nash equilibria. We know this is our second Nash equilibria. But this is what we're going to say, that in the very first game, we're going to decide to play our middle, middle. That's where we are going to be the best. So let's get a different color here. We'll do red. Red is going to be our middle, middle color. That's where we want to be. So playing middle, middle for the first game. So what happens next? In the second game, since you and I could have deviated and we didn't, we now trust each other. Because we now trust each other, we're now going to play the better option, which is right, right. So if we trust each other, we're going to play right, right, but only when the middle, middle was played in the first game. So round 1, we play middle, middle. Round 2, we play right, right. If any other option was played in the first round, so if we didn't play middle, middle, if we cheated somehow, then what would happen is we would result in the second game of penalizing each other. So we want to think of left, left as our penalty option. So penalty. This is reward. So now we need to determine, is our reward option better than our penalty option? If our reward option is better than our penalty option, then we will continue rewarding ourselves. We'll trust each other and we will play middle, middle the first game. But if our penalty option is greater than our reward option, then we will play our penalty option. We'll play anything other than middle to begin with. So we need to believe that this threat is credible, though. So how can we start analyzing this and understanding if these are better or worse? So if I were to cheat now, so by cheating, which means playing anything other than middle. So we're going to define cheating as player 1 playing left, where player 2 plays middle, which means player 1 would have earned a 5 in the first game. So now by earning 5 in the first game, we now need to penalize ourselves, which means that they're going to play left. The opponent is going to play left, and now I'm also going to get only 1 unit. So in total, my total payout for cheating is 6 units. So now I want to see if my total payout from colluding or cooperating is going to be better. So if we both play middle, I'm going to get 4. So this has to be middle 1, middle 2. So we've cooperated in the first game. So since we've cooperated, we now are going to get a payout of 4. But now, since I cooperated, I don't penalize ourselves. We're now going to play our reward option, which is 3-3. I now get an additional 3 units by both of us choosing right. And since we now get 3 units in total, my payout is 7. So by cooperating, I'm going to be better off by playing 7 than I am by actually cheating and getting 6 payout. So that's an interesting result. That means that in the beginning game, I can actually start playing middle. So what is this combined? So we want to think of this as the combined payout of all options. So for all actions. So we can see exactly what we just described, that 7-7 happens if we cooperate. And if anything else was played, we see this is exactly the outcome we would have gotten, a 6 here. And if we switched roles where player 2 deviated, they would have gotten here. And those would have been the likely deviating outcomes. But what happens if we play right to begin with? What happens if both players try to play right in the first game? Well, we realize by playing right in the first game, we're going to play 3-3, and then in the second game, we're going to have to be penalized and play 1-1. So in total, they get 4. And we realize that any choice results back to, except that middle option, any one of those choices gets penalized, and we go back to left. So we're always just going to add 1. We're always going to add 1 to our payouts, and that's why we get 2-2 here, because that means we played left twice. And that's why we get 1-1 here, because we're playing left-right, and we get nothing, and we then are penalized with playing left. And so we see that none of these combined payouts is greater than this middle payout if we would have just colluded. That's how we know that we can now play middle. This is the best option for us, and that's something that we want to actually play. And we can see kind of, again, how we constructed this outcome. So the prisoner's dilemma that we just faced, or the payout, the matrix that we just saw, basically, originally, if we played this only once, our mutually beneficial outcome wasn't there because there was such a great incentive to cheat. But when we played this game repeatedly, that just isn't the case. That incentive to cheat kind of falls away. It only falls away because there was credible threats, because that meant there was actually a penalty. So as long as there's a penalty enough that influences our current behavior, we'll change our current behavior. And really, what we ended up doing for this problem is using a strategy called backwards induction. Think of this as a chess player deciding what pieces to move. They think of backward induction as the motivating kind of algorithm for solving this problem. And that's exactly what we did. So in In class, we're going to be playing this centipede game. The centipede game is really interesting. For us, the centipede game just reflects two choices between two players that are now playing sequentially. So let's think about this game. So now the centipede game says we're going to have two players, player 1 and player 2. So player 1 is going to start off, and then they're going to wait for player 2 to play. And then player 1 plays again and player 2 plays, and they have two strategies. They could play quit the very first game. Player 1 can choose quit, or they can choose continue. Now, if player 1 decides to quit, he gets a payoff of 1, and player 2 gets a payoff of nothing. But if he chooses to continue, then player 2 has the option to now quit, which player 1 gets nothing, but player 2 gets 2 units. Or they can choose to continue, where then player 1 gets the option, and player 1 can choose to quit, where he would then get 3 units, and player 2 would get 1 unit. Or player 1 can choose to continue, where player 2 then gets nothing, but player 1 gets 2 units. And player 2 can also choose to stop the game by choosing the C option. And the C option, we see that if they chose this, player 2 would get 3, and player 1 would get 2. So what is the outcome? What is the Nash equilibrium of this game? Well, it's natural to think that we'll start playing through this game and stop maybe somewhere in the middle. But we're actually going to use backward induction. So for us, we look at player 2's last choice. So we're going to just subscript these. So this is player 1's first choice, player 2's first choice, player 1's second choice, player 2's second choice. So at player 2's second choice, we see that player 2 is going to choose the action to this C and continue because their payoff 3 is greater than nothing if they chose to quit, right? So we're comparing this and this value here. So knowing that, player 1 in their second choice knows that player 2 is going to choose C. So player 1 would like to actually choose Q. So player 1 is going to choose Q in their set here because they're going to get a payoff of 3 if they choose to end the game. And that's going to be bigger than the payout that they would have received if player 2 chooses the game at 2. Well, player 2, given their first choice, knows that they would stop the game at the end, and player 1 would choose quit. So they now have that option to observe, and so they are going to not let the game continue, but they're going to quit themselves because their payoff of 2 is greater than the payoff of 1, which would have happened if they let player 1 continue. And then player 1 in their first choice knows that in the very end of the game, player 2 would choose C, and that if given the option, they would have chosen Q, and that given the option of player 2, they would choose Q, so that player 1 actually is going to choose Q and choose to quit the game before even getting to the end. And that's because knowing that player 2 is going to choose to quit, their payoff is going to be greater. This 1 is greater than the 0 that they would have gotten if player 2 chooses to quit. So we actually end the game at the very beginning. That's not a very common solution that the average player picks. The average player tends to, if we were to play this 100 rounds between player 1 and player 2, we would actually end up getting to about the 50th or 60th round, whereas grandmasters in chess actually stop this in the first round. A study shows that 99.9% of all grandmasters stop it actually in the first round. Okay, so moving along from the centipede game, we want to talk just a little bit about some other games that we could see. Now, we have something called a zero-sum game. Now this means that whatever I lose, my opponent would have to win. So think of this as a lottery. Whatever I put up in the lottery, someone else is winning that. That is a zero-sum game. The prisoner's dilemma games that we've looked at before are not zero-sum. We can think about, in the real world, zero-sum games actually existing all the time. Think about maybe an example where we have, where essentially we have paper, rock, scissors, right? That's a zero-sum game. Whenever I lose, you win. Whenever we look at chess, whenever I lose, you win. These are all zero-sum games. And we talked a little bit about this idea of expected payoffs and calculating that, but we want to make sure we understand this just one more time, and that the expected value, or the expected payoff, is going to be comprised of our probabilities, P, so our probabilities of an action occurring, times the action itself and what we would win in that action. So we're going to sum up all of those different probabilities, and this is going to change and reflect different risk profiles for us. So what is another type of game that we can play? Well, we can look at a repeated game, but this is going to look a little differently than what we saw before. Before, what we looked at was something called a normal form game or a matrix form game, where right now we're going to look at something called an extensive form game. So this extensive form game was very similar to what we saw in the centipede game, and this is very much a sequential game. So what are some of the key characteristics here? Well, we have the beginning. The beginning is player A. So player A is at the root, and their root is the decisions that they can make. So player A can choose either yes or no. And then we get to two different what we call decision nodes. So player B is going to know what decision node that they're at. They're going to be able to observe, did player A say yes or did they say no? So being at each decision node required observing the branch no or the branch yes. So when player B chooses their branch, they can choose yes or no. Player B can choose yes or no. And then we'll get to what we call the terminal node. The terminal node is just the payoff from this game. So we can now kind of play this through backwards induction to understand exactly where our outcome would be. So let's play this. If player B, we want to look at player B's outcomes. Player B, we can see that they have two different outcomes here, that if they're at this decision node after player A had chosen yes, they're going to choose 20. And if they're at this decision node after player A had chosen no, they're going to choose 25. They're going to choose 25 because it's greater than this 0. They can't get back up to this 20 even if they wanted to, because player A chose no instead of choosing yes. So now player A needs to make a choice. Now, knowing what player B is going to choose in either instance, player A needs to look at these outcomes. So now player A realizes that if I were to say no, player B is going to say no, and my choice, my outcome is 10. But if I were to say yes, we know player B would then say yes, and my outcome is 15. So this is our preferable choice. Player A to say yes, and player B to say yes. So ultimately, we're going to get back up to this outcome. So we played that game using backwards induction. So let's try another one. So we have another game, but we're going to define something else. We're going to say that each decision node of player B constitutes something called a subgame. Now a subgame we're going to use through backwards induction just means that we can have player B make a choice, and then player A is going to be able to observe that. So player A, again, this is the same setup in the same game that we're seeing before. And so we can think of these as two separate subgames now. So player B in their subgame up here is going to, at node S2, we see is going to choose 20, where at node S3, player B is going to choose 25. And like we discussed, player A knows the outcome of each subgame. So Player A is going to choose the branch yes to get to player B's node S2, where they're also going to choose yes. And that is our payoff and our outcome of this game. That's our Nash equilibrium. So here's the new game that we want to discuss. So we can see that there's two subgames. We have two competitors, Macrosoft and Microcorp. So I'm just going to highlight again the subgames. So we want to use backwards induction again. So at this S2 and node S3, we're going to look at the choices from Microcorp. So Microcorp at node S2 is going to choose to stay out because they would rather get nothing than have to pay $250,000. And at node S3, Microcorp is going to choose enter. And they're going to choose enter because they would rather get $100,000 rather than zero. Well then, knowing that, Macrocorp or Macrosoft is going to look at each node and what are the payoffs then at S2? Well, we're going to see that they are going to rather choose $430,000 rather than the $400,000 if they were to choose to get to node S3. So what is the Nash equilibrium of the game? The Nash equilibrium is for Macrosoft to choose Slick and Microcorp to choose Stay Out. That is our Nash equilibrium of this game, and we call it subgame perfect, meaning that it works in every subgame. And that is kind of the most complicated type of game that we'll be introducing in class. So we saw a variety of different games here. We introduced some new terminology, and I hope we're able to kind of take this information out into the real world.